In the first exercise of the third session, we're asked to translate the following program from C to RISC assembly. This is a simple C program containing a simple function, a little bit more complex function, and then the main function. So the idea here is that you learn how to write a function, how to write a nested function as well, and to follow the calling conventions. So this is very important. I have this document here. You should have read the calling convention by now. And this specifies the method in which we will call functions in RISC-V. So this calling convention document, what this is basically the deal that different compiler writers and low-level programmers make with each other. They say, we're going to follow these conventions so that I can write a part of the code, someone else can write a different part, and they can easily link together. So if you don't, it's possible to write programs breaking these conventions. It's perfectly possible, it's just a very bad idea. Let us now look immediately at a solution. I don't want to repeat too much what I've already said in the intro video. So, if we would translate the simple function doublet, which takes an argument, an integer argument, as its first and only parameter, and it has one return value which is also an int. Now, when I want to translate that to RISC-V, well then I know one thing. I know the argument will be passed in A0. Why do I know this? Well, if I look at the calling conventions, we will see, so the RISC-V calling convention passes arguments in registers when possible. Up to 8 integer registers A0 to A7 and up to 8 floating point registers are used for this purpose. Now, I'm not going to read all of this for you, but for a simple int value, this fits into a register. Right here you can see an int is 4 bytes on RISC-V 32 bits, which is what we're working with. It's 4 bytes in size, which means it fits in a single register, which means you can pass the int through a register. There are exceptions for stuff like long, and we will see that in next exercises. But for now, we just have a simple function which takes an int. This fits into a register, so we can pass this int through a register. And we will pass the int through register A0, since it's the first parameter. If you would look at sum, we know that A will be an A0, B will be an A1. What we also know is that the return value of doublets and also of sum will be in A0 as well. So A0 is used both as an argument and as a return value. Great. With this in mind, we can actually already write the doublet function. The doublet function is very simple. A is an A0. The result should also be an A0. And the result should be 2 times A. So all we have to do in this function is execute A0 at A0, A0, A0. Right? I just removed an old instruction there that I had put there as an example during a session. So this is the implementation of doublet. You can have, we store 2 times A0 in A0. So because we know that the return value is an A0, and we know that the argument also is an A0, this is the correct implementation of the doublet function. Doublet does what it needs to do. Before I go into the sum function, which is the most complicated, let us now look at the other perspective. We've now looked at a function. We're just writing a function that needs to be called. Let's look at the perspective of calling a function. When we call the function sum, we know x here needs to be an A0, y needs to be an A1. Remember? The result after the execution of this function will be that the result will be an A0 again. So if we want to write this sum function, we load the value of x, which is in memory right here. We put it in the data section. We load it into A0. We load the value of y into A1. Now the parameters are in correct registers, so we are ready to call the function, we execute JIL sum, jump and link sum. This instruction will transfer control to the sum function and will also set the RA register. This one, the RA register, it will set the value to the address of the next instruction. So the instruction on line 33 here, this address will be stored in RA by executing sum. Why? Because when we return from a function, we want to continue on where we left off. That's why we store the address of the next line, so that we can return. So that's how we write this function call. And after this function call is complete, return will return to RA. RA will say, oh well, you have to return at this line. And at this line, after the function call, we know that the result of the sum is an A0. Now the C program wants us to put it into Z. So we store the value of A0 into the label Z. And we use a temporary register T0 to resolve the label Z. So A0 is stored into Z, which contains the result of the function sum. Great. Now we've seen how we call a function. You put the correct arguments in the correct registers, and then afterwards you get the result back from the correct register. All based on calling conventions. Now, the sum function is a little bit more complicated. The sum function is called by the main function and also calls a different function. And whenever you have this structure where you have a function that's being called, that means it's a callee, but also calls some other function, which means it's also a caller, you need to pay attention in these cases. So, let's take a step back and remember callee and caller safe registers. For callee safe registers means if you are being called, if you are the callee, think about who is the callee and who is the caller. When main calls sum, then main is the caller, sum is the callee. And the name of caller save and callee save says what you have to do. If you call a function, you're the caller. Then you have to save all the caller safe registers. And that's what we're going to do. So RA and A0 are caller safe registers. Now sum is the caller of doublets. So before the sum calls doublets, they will save all the caller safe registers. Because they are caller safe. The caller has to save them and sum is the caller. RA and A0. Now you don't need to save every single caller safe register. You need to save the caller safe registers for which you need the values afterwards. Why? Well, all of these values could be overwritten in doublets. All values of the caller safe registers could be overwritten in the function doublets. Thus, we have to save them if we want to make sure that we can use them after the function execution. So that's what we will do. And how we will save them? We will do this using the call stack. So, the call stack. First, we reserve 2 words on the call stack by decrementing with 8 bytes. Remember from the slides, the stack grows from high addresses to low addresses. So we decrement the stack pointer, which means we reserve space for 2 words, 2 times 4 bytes. And then at the first spot, we save the return address, and the next spot, we save the first argument of the sum function. These are the caller safe registers. Now that we've saved this argument on the stack, we have a backup on the stack. Now we can overwrite RA and A0 without worry. We will need the value of A0. We will need the first parameter of doublets. So we will need this parameter A afterwards. But only when we know the results, the first parameter of sum, we will need this after we got the result of doublet B. But for calling doublet B, we need to put a different value in A0. We need to put the value B in A0. Since doublet wants this in its parameter in A0 as well. That's what we do in this line 19. We move the value B, right here, which is an A1. We move that to A0 so that we can call doublets. So we call doublets. Now remember, calling doublets will cause the RA register to get a new value. the value of the next line of code, which is this line of code. So the address of this line of code on line 22 will be stored in the RA register. So to make sure we don't lose the alt value of RA, we had to also back this up on the stack. So since RA and A0 are overwritten in these two lines, we back them up on the stack first. These are caller safe registers. They will be overwritten, or they can be overwritten by the function that you call. Great. Then we call doublet, and when doublet is finished, we know the result of doublet will be in A0. So this, what I've marked here, the result of doublet will be in A0. The value of A currently is not anymore in A0. We overwrote that. In A0 right now is the value of doublet B. A lives on the stack. So let's get it back from the stack by loading it from the stack. Just like this. We load the value A in T0. And then we can sum that with what's in A0. So in A0 we have the value doublet B. And then in T0 we now have the value A. We sum those together and we store that result back into A0. So in the end, A0 here has the value A plus doublet B in this line of code. After this line, A0 will have the correct return value. And A0 is already the register where we need to pass the return value, so we're almost done. We have our return value ready, so now you want to actually return. But before you can actually return, you need to make sure you do two things. First of all, we need to restore our caller safe register RA in this case. We need to restore the return address because we overwrote the return address. If we would return right now, if we would put a return right here at line 24, let's do that. I'm not going to execute it. This would return back to line 22 and will go in an infinite loop because RA is still set to this line of code because we called doublets. We need to restore the alt value of RA, which points to this line of code on line 33. We do that by simply loading it from the stack where we backed it up. So now we are ready to return. And if we would return right here, we would indeed return to main. Our program would even work, but we would have an illegal function. This function would violate calling conventions. Why? Stack pointer is a callee safe register. What does that mean? That means if you are a function, if you write a function, you must guarantee as the function that callee safe registers have the same value at the beginning of the function and at the end of the function. So if you save SP, which is a callee safe register, if you change this in a function, you must restore this value at the end of the function. So you are obligated to do this because this is a callee safe register. So we don't need these values on the stack anymore. We've used the stack, we've backed up our values. Again, we pop the two values of the stack, we restore the stack pointer. This is a callee safe register. In this case, sum is the callee because main calls sum. And so sum is obligated to restore all of its callee safe registers. If we would have overwritten in sum, for example, if we would do li s01, then we would have to make sure that at the end of this function we could restore the value, the original value of s0. So before we could actually write this into a function, we would have to first back up the old value of s0 on the stack so that you could restore it later. Once we restored all of our callee safe registers, in this case only SP was modified from the callee safes, we restored all of them. Now we can safely return. RA is pointing to the correct return address. SP has been restored. We can return from sum back to main, and that's our program. So that's how we can translate simple C programs using calling conventions. Read this document. This is very important. You have to follow these calling conventions. You will be graded on this. If your code doesn't follow conventions, you will lose a lot of points. It's very important that you understand why this is necessary as well. And the second exercise will go into more detail. So let's go to the second exercise.